Hello, everyone. Come on in. The process of getting everybody in here. While we're waiting for people to log in, feel free to ask me any questions. All right, looks like I got some more people coming in now. That's cool. We got about 13 people. That's just about it. Now, we are starting. Last time we finished up chapter 17. I know I didn't cover every little detail, if you will. Uh, but like I told you, the most of that stuff is supposed to be stuff that you've probably already experienced. If you have any problems with it, make sure you let me know. But we're jumping into chapter 18 now. Uh, from now on, also remember that generally the homeworks are always due at 11:59 on the Sunday after they're assigned. When we go to spring break, though, for instance, we'll get a series of homeworks that are assigned the week before spring break. And then during spring break, you'll have all that week, but you also have the following week. So that's the one instance where it's not necessarily going to be a Sunday, but other than that, it's not going to be the immediate Sunday. But other than that, basically all your homeworks you want to get on the plan of basically assuming all your homeworks are due 11:59 on Sunday. So make sure you check that every Sunday just to make sure you don't miss any. And there always should be at least two, one for the chapter homework and one for the chapter conceptual questions. So anyone have any questions on any of that? You can also ask me questions about lab. If anything came up you didn't understand, you can also text me about that. That'd be fine as well. There's really no quote unquote wrong way to do it. If you're doing that lab and you find a way to draw your equal potential lines and then your E field lines, long as you have your equal potential lines and your E field lines for all the things that the lab write up asked for, then it'll be fine no matter what way you did it. So don't worry about that. All right. Well, it looks like I don't necessarily have any questions. So first off, I want to start off with, we're going to do a derivation in kinetic theory. So kinetic theory is where you basically uh, use the ideas of kinematics and stuff of that sort, dynamics, all those things, acting on particles as if they're, little point particles that are infinitely small. Conservative collisions is all that occurs, stuff like that. And in doing so, we're going to make use of the ideal gas law. In principle, you could be treating this as if it was a derivation of the ideal gas law. But in another sense, you can think of it as using the ideal gas law to come up with an expression for the kinetic energy of molecules or atoms in a substance. So in order to do this, I do need the ideal gas law. And specifically, I need a version of the ideal gas law that I didn't necessarily explicitly show you, but if you were at chapter 17, you already knew. So one of the ideal gas laws that you're used to showing, even though your book's using capital P, I usually use a lowercase p and a capital V, and that's equal to N times R times T. And that's fine. It does have the rules. Don't forget, must be Kelvin. This is a number of moles. And this must be total pressure or absolute pressure.
Mr.
Mr.
Younger,
Younger, are we sharing the screen?
This is twice today that I forgot to do that, but yes, we are sharing screen, only I chose to forget to do that. All right, appreciate that. Thanks for keeping me on my toes, guys. I don't know, I apologize. All right, it should be loading up pretty soon. which is good because I did some horrible handwriting and I can fix that now. All right. So as I said, that lowercase n is the number of moles. This P is absolute pressure, not gauge pressure. Okay. And then, of course, is the ideal gas constant. But there's also another version. It's P. Let me write that in blue again. The other version is PV equals capital N times Boltzmann constant times T, where N is the number of atoms / molecules, and KB is or K is often written as KB equals the Boltzmann constant. And that's 1.3807 times 10 to the negative 23rd joules per Kelvin. So if you think about it, N is really the mass divided by the molecular weight. That'll give you the number of moles. But you could actually get N by taking the number of moles and multiplying it by Avogadro's number. So if you look at it that way, then you could say that N is actually equal to, basically, I'm going to take the lowercase m, multiply it by Avogadro's number, and then divide it by the molecular weight m, like that. So that's a way you could do that. And if you then plug that in, say, to that second equation, what we'd see is there's a definite relationship between the ideal gas constant and the Boltzmann constant. You can look, R is 8.314 joules per mole Kelvin, and K is 1.3807 times 10 to the negative 23rd joules per Kelvin. So you see, if you actually multiplied by Avogadro's number, if you took K times NA, the person came in. Now, if we take that K times NA, that's 1.3807 e to the negative 23rd times 6.022 e to the 23rd. That gives me the 8.314 joules per mole Kelvin. So now that's the relationship. Evidently, R, the ideal gas constant, is just equal to Boltzmann constant times Avogadro's number. So that's an expression we'll use. This is a equation we've been using, and here's a question, an equation we'll be using as well. So hopefully you're on board with all that, because from here, we're now going to use that to actually analyze some particles, atoms, or molecules. And your book's going to mainly call them molecules, but I'll tell you, if you're dealing with an elemental gas, then it's actually not molecules you're dealing with, it'd be atoms. And that's fine. But like I said, we're going to repeatedly say atoms. Sometimes I'll say atoms and molecules, but the main thing is just know that they're saying molecules, because it includes a special case of a molecule, which is just an atom. So to do that, I'm going to have to use the ideal gas law, which I just showed you 2 versions of, and I'm going to do some derivations. But before I get started on that, I did want to read the chapter opening question, because you should always do your chapter or opening question as you start a chapter. So this chapter opening question, it says the typical speed of an air molecule at room temperature, 20 degrees Celsius, is what? And it gave you multiple choice answers like less than 10 kilometers per hour, B, about or on the order of 10 kilometers per hour, C, on the order of 100 kilometers per hour, D, on the order of 1,000 kilometers per hour, or E, nearly the speed of light. So hopefully you've had enough experience in your life between chemistry, physics, physical science, earth science, and all that good stuff. You have some idea roughly what the average speed of the molecules are in air at 20 degrees Celsius. But if you don't, that's okay. The best thing is for you to make an approximation or make a guess using whatever tools you have at your disposal in your head. Again, not Googling it, but make a guess. And then when you find out the right answer, then either pat yourself on the back for figuring it out or figure out where your reasoning went wrong. But the main thing is that gives you sort of a focal point as we're covering the material. So in this section, what I'm going to go ahead and do is I'm going to draw a coordinate system. And I'll draw that as my z-axis. I'll draw that as my x-axis. And then to keep the axis right-handed, I'm going to draw the y-axis into the board. So I have right here the x-axis, right here I have the y-axis going into the screen, and up here I have the z-axis. And now what I'm going to do is I'm going to put a little box on here. So let's imagine that our box is right here. That appears to be about 6 units long. Whoa. Now I'm going to draw another one. 1, 2, 3, 4, 5, 6. That's about right there. And now what I'm going to do is represent the box as this. Okay. So what I'm going to say is that this box has a width L, and I'm also going to say that it has a area on the right face and left face equal to A, like that. Okay. And now in this, we're going to have a bunch of little molecules. Again, they're using the word molecules, but it could in fact be the atoms as well. They're going to be going in random directions. And in fact, I'm going to focus on a particular molecule. And the molecule has a mass M. And it's going to bounce off the wall here. And then leave with another velocity like that. So that's what I'm investigating. Now, in order to do this, I need to establish some rules. And I can tell you them. I'm not going to take the time to write them down, but you can actually turn it to section 18.1 of your textbook, and we'll express to you the basic postulates of kinetic theory for an ideal gas. Okay, here are the postulates. I'm going to read them to you. So make sure you pay somewhat attention so you can make sense of why I do what I do in the next couple lines. But the first rule is there are a large number of molecules, capital N, that's the number of molecules, each of mass, lowercase m, that's the mass of each molecule, moving in random directions with a variety of speeds. This assumption agrees with our observation that a gas fills its container, and in the case of air on Earth, is kept from escaping only by the force of gravity. Okay, so that's the first rule. The second rule, molecules are, on average, far apart from one another. That is, their average separation is much greater than the diameter of each molecule. 3, molecules are assumed to obey the laws of classical mechanics and are assumed to interact with one another only when they collide. Although molecules do exert weak attractive forces on each other between collisions, the potential energy associated with these forces is small compared to the kinetic energy. So we're going on the assumption that the attractive forces and potentials caused by those forces are very small compared to the kinetic energy. Therefore, we can ignore them. And then number 4, collisions with another molecule or the wall of the vessel are assumed to be perfectly elastic, like the collisions of perfectly elastic billiard balls from chapter 9. We assume the collisions are of a very short duration compared to the time between collisions. Then we could ignore the potential energy associated with the collisions in comparison to the kinetic energy between the collisions. So that's what we're shooting for. Now, what I'm trying to do here with this box is I am trying to calculate exactly what the pressure is on the, let's say, the left face. And then I'm going to try to relate that to quantities like capital N, lowercase m, pressure, volume, all that good stuff. So in order to do it, I first need the force. And according to Newton's second law, we know that the summation of the forces is equal to dp dt. I like using this version here, which is the more general version of Newton's second law. But in this case, because of those 4 assumptions, we've already reached the conclusion that basically the only force we're worrying about is the force that the wall applies to the molecules, or that the molecules apply to the walls. So we don't have to think too much about a sum of forces. We just have to think about the force that the wall applies, or excuse me, the force that the molecule applies to the wall. So I'll separate that and just say F, rather than just saying summation of forces. I'll just say F is equal to approximately delta P over delta T. Now, to make that an actual equals as opposed to approximately equal, you're obviously going to have to take the limit as delta T approaches 0. And what we're going to do is find the amount of time, delta T, required for this molecule here that I've drawn. How long is it going to take between it hitting the wall and then hitting that same wall again? So first off, I'm going to calculate the change in momentum. And remember, P is equal to M times V. Now, what I'm thinking about is really this particle here has a X component of velocity, which I can draw this way. It has a Y component of velocity, which I can draw this way. And it has a Z component of velocity that way. But notice, because these collisions are elastic, when this molecule hits that wall, it's not going to affect the Z component of the velocity, nor is it going to affect the Y component of the velocity. And the only thing it's going to do to the X component of velocity is change its direction, because 4 said that the collisions are elastic. So if the kinetic energy of the system was 1/2 mvx squared before it hit the wall, then after it hit the wall should be the exact same 1/2 mvx squared again. So you know the Vx can only change sign. So with that in mind, this is P final, and this is P initial. So I'm going to talk about P sub x specifically. And what I'm going to do is I'm going to say the final is M V sub x in the positive direction minus the initial, which is negative M V sub x in the negative direction. That's why the negative's there. So you get 2M V sub x. So that's what conservation of momentum, or what the change in momentum will be as a result of that molecule bouncing off the left face, which initially was hitting in the negative x direction, and then bouncing off in the positive x direction. Okay, but that's only the x component. Now, if you wait long enough, this mass is going to bounce off that wall, and it's got an upward trajectory as well as a y trajectory and a z trajectory. But the fact that it's upper means it might hit the right face first and then hit the top, or it might actually hit the top and then hit the right face. But the main thing is that's only going to affect the velocity component in the z direction, and it's just going to change its sign. So it doesn't slow it up in the x direction at all. So we can now use that to realize that the time, which remember velocity equals distance divided by time, the time between that first collision when it hit the left wall and the time required for it to bounce off the right wall and return is basically, since we're dealing with just the x component, it's just the x component of the width divided by the x component of the velocity. So it's going to take a distance L to get to the right face, and then it's going to take a distance L the other direction to get to the left face again. So the delta T is going to be 2L over the x component of velocity, which is v sub x. Does everybody understand that? This mass is going to be going bing, 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 but it's never going to slow down or speed up in the left direction. It's just constantly going back and forth where it bounces off the top face. Sometimes it bounces off the back face. Sometimes it bounces off the front face. Sometimes it bounces off the bottom face, but it's always going to return to the left face again after a time 2L over v sub x. All right. So putting that together, we can reach the conclusion that F is going to be equal to 2m v sub x over 2L divided by v sub x. Of course, the m's cancel out now, or excuse me, the 2's cancel out now, and we end up getting m v sub x squared over L. Now that's the force due to exactly one molecule. Okay. In fact, we're not going to have one molecule. We're actually going to have n molecules. So if I subscript this one particle with the number 1, and then I just imagine another particle is going to be number 2, and another particle is going to be number 3, and I keep going all the way up to get n, then what I'd say is F total would be equal to, in this case, it's going to be m over L times v1 sub x squared plus v2 sub x squared plus v3 sub x squared plus dot 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 plus vn sub x squared again. Okay. Now we need to think not only about all the particles, but the velocity in general, because it's, we're not necessarily that interested in the velocity in the x direction or velocity in the y direction or velocity in the z direction, but we really are kind of interested in the total velocity. What we know is that v squared is equal to and I'll put an I on it just to represent the ith particle. That's equal to v sub I x squared plus v sub I y squared plus v sub z, v sub I z squared as well. Okay. Not only that, there's no preferred. Yeah, go ahead, Mark.
Sorry to interrupt. Can you explain again why all of this is in terms of x? Like you're getting to v sub y and z, but like for our total force, it's just using x.
So what I'm trying to do is reduce it to a particular face so that I can calculate the force on that one face. And if I calculate the force and therefore the pressure on that one face, and it ultimately gives me a relationship for everything, then by symmetry, we know that that one face is not special. So I could also apply it to the top face. I could also apply it to the bottom face, the front face, the back face, and the right face. So we're actually doing, even though it seems like we're just focusing on one, we're actually doing the very general process of any face.
Okay. Yeah, that makes
Okay.
sense.
So yeah, I'm just doing that. Now we know that the total velocity squared is the sum of the squares of the components, but we also know that there's no preferred direction. There's no reason that the atoms on average should be going much faster in the x direction than they are in the y, and let's say way faster still in the z. That wouldn't make any sense. In fact, there's something called the equipartition theorem that says that basically when you give a tranche of energy to a system, a very complex system like this with a lot of things, there's no reason to assume that any one type of energy gets the lion's share of it. In fact, the equipartition theorem says that every different type of energy it can go in, an equal amount will go in there. So with that in mind, we can also say that VI sub x squared is also equal to VI sub y squared, and that's also equal to VI sub z squared. In other words, uh, there's no reason to think Vx is bigger than Vy or Vy is bigger than Vz or vice versa. They should all be equal. So if we look at it that way, then we can reach the conclusion that Vi squared would actually be equal to 3 times Vi sub x squared. Does that make sense? Because there's one for x, there's one for y, there's one for z, so that's the 3. So now I have F total is equal to, we had reached the conclusion that it'd be M over L times, and that's an L. Let me make that L a little better. It's starting to look like a lowercase e now. So that's V1 x squared plus V2 x squared plus dot 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 plus Vn x squared. Now, what we're going to find out is that Vi squared on average would be V1 x squared plus V2 x squared plus dot 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 plus Vn x squared, all that divided by n. And we already have this quantity right here. So now we can say that this is just equal to n times m over L times V squared with a bar over it. Okay. So in other words, we're actually taking that average. Any questions on that? And actually at this point, it should be just plain X. So I'll put the X there. Now I'm going to make use of the fact that, as I said right here, Vi sub x squared times 3 is equal to V sub I. So I can replace the V sub I x squared. I can replace that with 1/3 V sub I. So now I get n times m over, well, actually, let me do it on another line because I'm clearly running out of space there. So now I can say F total is equal to 1/3 n times m over L times V squared. So now I've gotten rid of not only the subscripts for the particles, but I've also gotten rid of the subscript x because I'm dealing with whole velocity at this point. Does that make sense to everyone? So that gives us the pressure, and remember, this is happening very rapidly. The particle will bounce against the left wall. It's going to do a bunch of stuff, and they'll come back and bounce against the left wall again, do some stuff, bounce again, but that interval should be very, very small. And the number of particles is on the order of Avogadro's number. So you're constantly going to be bombarded. So it'll feel like a fairly constant force, even though in principle it should be a bunch of little discrete forces. So now what I need to do is I need to use the definition of pressure. So pressure is defined to be the force divided by the area perpendicular to the force, at least in the way that I'm dealing with it now. So if I want to calculate that, then I'm going to take that F total and divide it by the area of the face that it's bouncing off of. So now I can say that P is equal to 1/3 N M B squared with a bar over it times A times L. Does everybody see? I just used the A from the diagram. Remember the A? I said that face on the left and the face on the right were actually had an area A. So now I've got that. You can actually take this and make it equal to 1/3. Whoa, I don't know why I keep wanting to write a 2 there. 1/3 N times M V bars or V squared bar. I'm going to multiply by 2 and multiply by 1/2 at the same time. So that's going to give me 2/3 by multiplying by 2 n, and then that's going to give me 1/2 by dividing by 2. And in doing that, now I get an expression that's kind of helpful to me. Okay. Everybody follow what I did there? All right. So
Mr. Younger.
go ahead.
Just before we get too far, where the 1/3 come from again?
The 1/3 came from the fact that we were just talking about the force on the left face, and that's only due to the x component of velocity. But in general, the pressure on the face is all the x components of velocity,
Right.
for all of them. And then what we had to do was we had to divide it by the area that gave you that. But the problem is we want it in terms of the total velocity. And because there's a symmetry between the x direction, the y direction, and the z direction, we expect each of those to contribute the same amount to the velocity, so that each one is 1/3 of the total velocity.
Okay. Thank you.
Does that make sense? Each one
Yeah.
squared is 1/3. So that's where the third came from. Now I can make use of the fact that we had PV equals NKT, and P is, oops, also I forgot something on it on this part over here. Let's do that. Anybody want to tell me what A times L is from that original diagram?
Volume?
Yes, it is the volume. And because we got a V in there already, I'm going to make it like that just to make sure we know it's a slightly different one. So in this case, we get P equals 2/3 N over volume times 1/2 mv squared bar. The bar again just means average. So I can combine these two and reach the conclusion that P times V, again, this V being the volume, is equal to, notice when I set these two equal to each other, I get NKT is equal to 2/3 N times 1/2 mv squared bar, like that. And you can see that the ends cancel out. So that tells us that we can now say PV, which is the left-hand side, is also supposed to equal, in this case, it's going to be 2/3. Oops, let me. It's going to be 2/3. We've gotten rid of the n, but we are going to have the k times t. And that PV is also going to be equal to 1/2 mv squared bar, like that.
Wouldn't it be 3/2 KT?
Oh, excuse me. Yeah, I put it on the other side and forgot to flip it. Thanks for catching that, Darren. I think that was Darren. Ah, not letting me shrink my page down again. Okay. So that's basically what we have. Another way of writing this is I'll write it in blue. And basically what we're saying is the average kinetic energy, because 1/2 mv squared is the kinetic energy, right? So that average kinetic energy is in fact 1/2 the mass times the average of the square of the velocity, but that's also equal to 3/2 kT. So that's what we're shooting for. That was the big result that we wanted. And now we can do things like I can explain to you when I was doing the atomic theory of matter, I told you that things move in such a way that as the temperature rises, so does their kinetic energy. Specifically speaking, it's the translational kinetic energy. So for instance, if you have a molecule that's like a dumbbell, where it's an atom and an atom separated by a bond, they could rotate this way. That's rotational, not translational motion. They could also rotate this way. That's rotational motion as well, not translational. So neither of those count in the temperature. And they could also rotate this way. That one doesn't count for much anyways, because you're literally just forcing something, the radius of which is about the radius of an atom to spin. So that one doesn't even come into play. The main thing is those two other quote unquote degrees of freedom, its ability to rotate this way and its ability to rotate this way, those two don't count in the calculus of determining the temperature. It's only the one that takes the molecule left, right, in, out, or up, down. Okay. Turns out there's other degrees of freedom, like where they can compress. So when they're going like this, that's another type of motion, and that's another degree of freedom. But technically speaking, not translational. So we now have the direct proof of that. Specifically, what I told you was that if you are, and let me sort of build this model in your head. If you walked up to a person and you could stop time, okay, and then while you've got time stopped, you go and survey every molecule or atom in their entire body, okay? And you say quickly, what's your mass and what's your average velocity? That's all the numbers you need. What's your mass? What's your average velocity? And they give it to you. And then you write it down and then you say that's, molecule or atom one. And you calculate 1/2 times m times v squared, which is the square of the average velocity. Okay. And you write that down in your ledger. Now you go to the second atom or molecule, do the same thing, go to the third, go to the fourth, keep on doing that. When you've done all the atoms and molecules in the body, and then you take the average of that, all you have to do is multiply that by 2/3 and then divide that by a Boltzmann constant, and you will have the body temperature of that person in Kelvin. Okay. So that is the very definition of temperature. It's the average kinetic energy of the molecules making something up. So as an example, let's say what is the average translational kinetic energy of the molecules in an ideal gas and let's say at I'm going to say whoa Nelly, I'm going to say erase a bunch of stuff and then start over at 50.0 degrees Celsius. So that's the question I'm asking. What's the average kinetic energy? Well, what I know is the average kinetic energy is 1/2 mv squared bar, but I also know that's 3/2 k times t. Okay. So if I actually had the mass, I could then use that to determine the average of the square of the velocity. And if you took the square root of that, that would be what we call the root mean square. And we're going to talk about that a little bit later. But right now, we're just asked for the molecule's kinetic energy. And without any knowledge of what kind of molecule it was, we can't figure out the mass. Therefore, we can only figure out the kinetic energy. So in this case, I'm going to say this is equal to 3/2 times 1.3807 times 10 to the negative 23rd joules per Kelvin. And then the key part is, remember, this came from the ideal gas law, and the ideal gas law requires us to use absolute temperature. So we have to use the Kelvin scale. And to get from Kelvin or from Celsius to Kelvin, you have to add 273.15. So if I add 50 to 273, that gives me 323. 0.15, and I just included the 0.15 because that's what I'm used to doing. You obviously don't need that many sig figs. I would always, just as a rule of thumb, I would always use one extra sig fig on any figures you used if you could. If you couldn't, just use the same number of sig figs, but you should always want one extra sig fig until the very end. So what I'm going to do is I'm going to say 1.5 because that's 3/2 times 1.3807 e to the negative 23, and then times plus 323.15. That gives me 6.63. And I'm going to carry one extra sig fig. The next digit is 0 followed by a 4. So I'm just going to put a 0 there. And that's times 10 to the negative 21 joules. So that's really what it is. If you imagine, for instance, a 1 kilogram stone, you could set that equal to that. And if you take the 6.63 times 10 to the negative 21, if I then multiply that by 2, because I'm solving for the velocity of this 1 kilogram stone, so I'm going to multiply it by 2 because I'm setting it equal to 1/2 mv squared. And now I'm going to divide it by the mass of the 1 kilogram stone, which is 1 kilogram. So that just gives me that. And then I take the square root of that. What I'd find is that gives you about 3,860 joules. So that corresponds to like a stone traveling at 90 meters per second. That's pretty fast. So just imagine a mole of these suckers. That's what that would do. So your book does that in the example. This is the right answer. So 1 mole would imply that the total kinetic energy would equal 6.022 times 10 to the 23rd. And that'll be per mole. And then we multiply that by 6.63 times 10 to the negative 21 joules. So what I'm going to get here is I get 3,992 joules. Oops, wrote it too small. Ah, dang it. So that's an extra sig fig in there. The 0 is an extra sig fig in there. So that's how much kinetic energy a whole mole would have. Now, a mole of gas, of course, is Avogadro's number of particles, and that gives you a real physical characteristic of how big the energy is. And what your author does is then says, let's let 1/2 times 1 kilogram times v squared equal to 3990 joules, and then v would be equal to V would be about 90 meters per second. So a 2.2 pound stone thrown at 90 meters per second, which is pretty darn fast, okay, has about the same kinetic energy as all those atoms and molecules bouncing off that one wall. So that's a pretty big deal. And that's kind of a nice little calculation to give you some estimate of how much energy that really is. Anybody have any questions on that one? All right, so now I'm going to address the chapter opening question with another example. Whoa, no. So here's another example. What is the RMS speed of the oxygen and nitrogen molecules of or let's say in our atmosphere if the temperature is 20.0 degrees Celsius. So that is exactly the chapter opening question, because of course the most prevalent gases in our atmosphere is nitrogen and oxygen. Oxygen is about 20%, nitrogen is very close to 80%. Of course, there's water vapor, there's argon, there's all sorts of stuff in there, CO2, CO, all that good stuff. But those are the lion's share. So what I know is 1/2 m times the average of the square of the velocity is equal to 3/2 k times t. And I'll say VRMS is the square root of V squared bar. So that's what RMS is. It's root mean square. So it's another averaging process that you might not be familiar with, but it comes in handy, especially if you are trying to deal with something that has both positives and negatives. So if you average, a bunch of numbers and they all had positives and negatives, then if they are randomly distributed or random numbers, the average is always going to be 0, because there's just as much negative as there is positive. So those are going to cancel out and give you 0. But what you can do to avoid that is instead take the average of the squares. So you square each number, that makes each one of them positive. You add all those squares up and you divide it by the number of particles. That gives you the root mean, or that gives you the mean square. And then, of course, to get back to units, the regular units, you take the square root of that. So that's what we're going to do. If I look at these two equations, I can see that 1/2, I can see that 1/2 mv squared bar is equal to 3/2 kt, means that this 1/2 can cancel out on both sides. And in fact, what I'm going to ultimately get is v bar squared is equal to 3 kt over m, which means VRMS is equal to the square root of 3 kt over m. And that's what I'm going to calculate. That's what I'm going to use it for. So first off, let's see oxygen. Okay, the molecular weight of oxygen is actually 16.0 approximately, and the molecular weight of nitrogen is approximately 14.0. Okay, so we're going to make use of that. But what I'm going to do is I'm going to say VRMS for O2 is equal to the square root of 3 times 1.3807 times 10 to the negative 23rd joules per Kelvin. Now at 20 degrees, that becomes 293.15 Kelvin. And then I divide all that by the mass, which, remember, it's O2. So the mass is not 16, but 32. Whoa. But 32. Come on now. 0.0, and that's a unified atomic mass units times 1.6605 times 10 to the negative 27th kilograms per U. Okay, so you should be able to see that this U cancels out with that U. This Kelvin, which is not all that well drawn down here, that Kelvin cancels out with this Kelvin, and all we have left is joules divided by kilograms. But a joule is a kilogram meter squared per second squared. So if I divide it by kilograms, I'm just left with meter squared per second squared. And when I take the square root of that, I get meters per second. And in fact, the answer is 510.4. I'll double check that calculation just to make sure. It looks like I got everything right. Ooh. Oh yeah, I misremember. Sorry, it's 478.03. I was remembering the other answer. 478.0 meters per second. That's with one extra sig fig. Now, if I wanted to, I could convert that kilometers to kilometers per hour by dividing by 1,000 to make the meters into kilometers, and then multiplying by 3,600 to make the seconds into hours. So basically just multiplying that by 3.6 gives me 478.0 times 3.6, and I'll call that kilometers per hour per meter per second. That gives me 1,720 kilometers per hour. So you should see now that the concept question, the opening question for the chapter, the right answer should have been on the order of 1,000 kilometers per hour. Any questions on that? All right, why don't you guys give the nitrogen a try? I'll do it as well, and we'll see if we get the same answers. So try to pay no attention to me until you actually figure out what the answer is. Unless you just can't get started, then you look for a second and then look away and try some more. All right, was everybody able to get around 510, 511? Anybody have any questions on that? Let me ask you a question. We've now figured out a way to compute the average kinetic energy of a molecule. Can anybody tell, based on this idea, that this derivation that we did here, what would the velocity or what would the kinetic energy of molecules be if the temperature reached 0 Kelvin?
It would be
Exactly. So we expect these things to slow down quite a bit as the temperature decreases. But in fact, quantum mechanics has taught us that that's not really correct. And to be honest with you, really shouldn't have even made such a attempt at using that equation for that scenario. Because remember, the ideal gas law is made up for conditions that match those first four conditions I gave you when I was deriving the kinetic theory, specifically that the forces are just collisional and kinetic energy is conserved. If you start to get down to such a low temperature that the thing considers the atoms getting so close that they could form into a liquid and then even into a solid, then you're definitely outside of the realm of ideal gases. Ideal gases are not supposed to be representative of gases when they're about to change state. So, yeah, Mark, you have a question?
Yeah, for oxygen, your fraction you set up, where did you get 32.0 U from?
Oxygen 16, it's like 15.9994. So I rounded that to 16.0, but oxygen, like hydrogen and nitrogen, are diatomic molecules. So they're naturally occurring in our atmosphere as H2, O2, and N2. So the actual molecule has two oxygens, and one oxygen weighs 16 unified atomic mass units. So two of them weighs 32.
Okay, will that be given for most things?
I think they sort of expect you to know that O2, H2, and N2 are diatomic, but you would definitely get a periodic table.
Sweet, thank you.
Okay. In this one, they did actually say O2 and N2, so that is giving you a little bit of a hint. I probably would stick to the same thing, but I think in general, we're starting to get to the point where we're supposed to be good enough in science that we know oxygen and nitrogen and hydrogen all come as O2. Helium does not, for instance. But anyways, any questions on that? All right, so I wanted to give you a little feel for exactly what this root mean square is. So in order to do that, I'm going to have you do a quick little calculation, or I'm going to do a quick little calculation. So example. Whoa. What is the average of the first 5 integers? And obviously, I mean 1, 2, 3, 4, 5. And 2, what is the square root of the average of the squares of those integers? So I wrote it that way so you know prescriptively what you're actually calculating. So at the end of the day, the part B, we're just asking for the root mean square. Okay, but I just spelled it out that way. So here's our solution. So I'll call this part A and I'll call this part B. So A, I'm going to say X bar, which that's one of the symbols we use. And here's another symbol we use for average is we put it in less than and greater than brackets. But in this case, it's going to be 1 plus 2, which is 3, plus 3, which is 6, plus 4, which is 10, plus 5, which is 15. And we divide that by 5 and we get 3.0. So that's the average for part A. For part B, it's a little more complicated. What we want is x squared bar square root, which equals x RMS. And that's going to be a square root of 1 squared, which is 1, plus 2 squared, which is 4. 4 plus 1 is 5, plus 3 squared, which is 9. That means we're getting up to 14, plus 4 squared, which is 16. That means we're up to 30, plus 5 squared, which is 25, which means we're up to 55. And then all of that divided by 5, that's going to be the square root of 55 over 5, which is the square root of 11. And the square root of 11, I think, is 3.16. Yeah, 3.316. And I'll call that 3.317. So you can see that, yes, this root mean square is a little bit larger than the regular average, but now you also know how it's calculated. Does that make sense to everyone? All right, so that gave us a nice little formula that we can use to calculate the average speed of the molecules, the kinetic energy of the molecules, all sorts of good stuff like that. We've learned that, yeah, as the temperature approaches 0, that formula would predict that they come to a complete stop. But in fact, even if you just saw The Incredibles, you know that things have a 0-point energy, right? And that's actually from a quantum state. But we learned, for instance, that the harmonic oscillator in quantum mechanics has a minimum energy of 1/2 h bar omega, or 1/2 h times f, and it will never go lower than that. You just can't do that. And of course, that's what they did in The Incredibles. Is the nerdy fanboy who became the villain actually figured out how to tap the 0-point energy and make his own instrument. And of course, that's completely apocryphal as far as we know, but it is still interesting. So any questions on that? All right, so that gives you a good idea. It's not necessarily the most accurate way. In other words, that's kinetic theory, and that was a quick and dirty, easy little derivation. But if you actually did a statistical analysis, there's a branch of physics called statistical mechanics. And there's also a branch called statistical thermodynamics, and there's also a branch called thermodynamics. And thermodynamics was probably my least favorite, even though it's very powerful and very helpful. Thermodynamics is probably my least favorite physics. Statistics is definitely my least favorite math. So as you can imagine, when I got to statistical thermodynamics, it was just awful and I didn't like it. But that's the kind of thing you would do in this. And some people call those two things interchangeably, statistical thermodynamics and statistical mechanics. But James Clerk Maxwell, the creator of Maxwell's equations, among other things, other than just creating the Maxwell's equations, he did a lot of stuff. He was a brilliant man. He was the Lucasian Chair of Mathematics at Cambridge University. That meant that he took the same position that Newton used to hold. And even though he got in that position, he didn't have that much respect from his peers in the scientific community, specifically because there's a testing procedure that goes on in at Cambridge University. I'm not sure they still do it now, but I know we would not allow this at all in America. But basically, at the end of your 4 years, there's a test called the Wrangler test, and it tests you on all mathematics, sciences, physics. Of course, in his time, they didn't necessarily even, they were just starting to use the word physics in his time. It wasn't around in Newton's time, but they had this Wrangler test, and it was a nasty test. Like, it would last, on the order of 6 to 8 hours for you to take it, and then they grade it. And when they finished it, they would put everybody's score on a big public announcement on a wall. And the person that got first place would be the Wrangler, and he would be at the top of the list. And the second place person would be the second Wrangler, and they would be in the second slot and all the way down. And you can imagine, we just don't allow that here in America. But that is definitely a way to compel people to do very well. In fact, many people back in that day made a whole living just by tutoring extremely wealthy parents, tutoring extremely wealthy kids for their parents, just to pass that test and to do really well. And in fact, the guy that beat out James Clerk Maxwell and got the Wrangler that time became such a person. He was a person that just did that. And he really didn't contribute that much to math or science ever again. And in fact, there's actually 3 different tests that go on, and he beat Maxwell in that test. Maxwell beat him in the other 2. So Maxwell still came across it. But in general, anybody that's in the area of Great Britain would have, especially working in the science, would have thought a little less of Maxwell because he didn't get the Wrangler rating, but he did get the second Wrangler. And like I said, he did win the other 2 major things. So he wasn't dumb by any stretch of the imagination. He was, in fact, brilliant. So in his time, he is exactly the person that allowed us the RGB color designation that we use now on computers. You know how we have a certain number of digits that we use for reds and blues and greens, and we use a hexadecimal for that. That whole system was entirely created by James Clerk Maxwell. He also created the Maxwell equations, which mostly he was able to just to copy from Michael Faraday's notebook, which had Michael Faraday, even though he wasn't a mathematician, he explained everything with such perfect detail that it was easy to convert it to a mathematical equation. And so Maxwell did, and was able to write out Maxwell's equations, but he was also able to figure out that one equation couldn't quite be right, and he fixed that as well. And between that and the fact that, he wrote them all together and absorb the consistency, allows us to call them Maxwell's equations. But really what happened was he did that. He did it in a very sort of obscure way, meaning he was using the variables that a lot of experimentalists used at the time. And unless you were working in that field, you didn't necessarily understand that. As a sidebar, his friend Hamilton had invented these numbers called quaternions, and he also put it in quaternion form, which made it even less tractable because quaternions no one uses now. I mean, I've heard of people doing a master's thesis or something by converting some major equation to quaternions, but we really don't use them at all. So they ended up, even though they were the pride of Hamilton, the great mathematician, they were not turned out to be anything that important, but important enough for him to put the rules of them on his tombstone. So Maxwell wrote all that, and he didn't get the respect of his peers from those equations, partly because they couldn't follow it. They had vector potentials and all sorts of weird terms. Then they had quaternions, which nobody knew. So nobody really were giving you very good are giving him very much credit for what he did in electricity and magnetism until Oliver Heaviside, and there's a whole history written in a book called The Maxwellians, where Heaviside and 2 or 3 other people got together and made Maxwell's equations super famous by converting them all to vector calculus, and not only that, teaching everybody vector calculus. So those are the ones that actually made it full. But in addition to that, Maxwell also was the first person to be accurately predict exactly what the rings of Saturn were. People thought at that time they might be actual disks. He showed that they had to be particles, and he gave us some very distinct properties about it. He also was able to come up with this, which I'm getting ready to show you now, and it's called the Maxwell distribution. So this is the Maxwell distribution. And it's basically a function that allows you to figure out for a given velocity at a certain temperature what fraction of the molecules in that sample have what velocities. So the Maxwell distribution is f of v, where v is the velocity. That's equal to 4 pi times n, the total number of particles, multiplied by m over 2 pi kt. That is raised to the 3/2 power. And then all this is multiplied by v squared times e to the negative 1/2 mv squared over kt. So that's the Maxwell that's the Maxwell distribution. And what it means is that f of v times dv is, actually, let me write it a better way, is the percentage r, yeah. F of v dv is actually, I shouldn't say percentage, I should say number, is the number of molecules of the sample that have there I go again, put the H too close, a velocity between v and v plus dv. Okay, that gives you the number. And because of that, you can see that the integral from 0 to infinity of, well, actually, let's go ahead and write it in the simpler way first, of f of v dv, which equals the integral 4 pi n m 2 kt, or 2 pi kt, sorry, I left a pi out there, to the 3/2 power times v squared e to the negative 1/2 mv squared over kt. And that's just a plain t there, so I need to make sure that was fixed, times dv, like that. Anybody want to guess what that answer should turn out to be?
One.
Very close. The difference is this. It's got to be n, because remember I said the number of particles or number of molecules. So basically what happens when I integrate from 0 to infinity is I am trying to compute the number of particles that have a velocity between 0 and infinity. And since we set out with the assumption that the whole object has, or the whole sample has capital N molecules, then, and the fact that we're going from 0, the absolute smallest possible velocity, to infinity, the absolute largest possible velocity, should read us that all of the N come out of that. And that is the truth. Okay. So that's one thing. Now, another thing is if you wanted to calculate, for instance, the average velocity, then you could take the integral from 0 to infinity of f of v times times dv. That's how you'd calculate the actual average velocity. Of course, that f of v dv is going to give you v times the number of particles. So there's a little bit of a process that has to go after that. Specifically, when you actually go to do that, you're going to have to take that integral and divide it by n again, because that's what the default is for the number of particles. So we're going to actually get that and just divide it by n, and that'll tell us what percent are in there. If you wanted to calculate not the average velocity, but instead the average of the square of the velocity, then what you're going to do is take the integral from 0 to infinity of f of v squared dv. So you could also do that as well. And in principle, that should come out to the 3/2 kt. Or excuse me, to the square root of 3 kt over m. So those are different ones. If I were to actually make a plot of this function, this Boltzmann, or excuse me, this Maxwell distribution, if I made a plot of that like this, what it would look like is something like this, where on the horizontal axis, I got various speeds, v, and on the vertical axis, I have the relative number of molecules. Okay. This graph would tend to look something like this. It's sort of steep on the front side, and then it peaks, and then it gradually falls down, something like that. And in fact, if you take the center of that peak, that's V sub p, which means the most probable velocity. So V sub p equals most probable speed. V bar equals the mean speed. And V bar squared square root equals VRMS. What we see here is that with this graph, you're going to have the peak up there at the top. That's VP. Now, slightly askew of that, because it's not symmetric. That means more of the weight is going to be to the right of that peak. So right about here is going to be V bar. And as we learned, VRMS is generally a little bit bigger than VR. So that's going to be VRMS right there. Okay. Now, I've just shown you what you could do to calculate V bar and to calculate V bar squared. I will tell you that the results are V most probable is equal to, this one's actually kind of easy. It turns out to be the square root of 2 kt over m, which is approximately 1.414 square root kt over m. The V bar turns out to be actually quite a bit more complicated. That's 8 over pi times kt over m, which is approximately 1.60 times the square root kt over m. And of course, we already learned that v root mean square is actually equal to the square root of 3 kt over m, which is approximately 1.73 square root kt over m. So if I ask you to do these, I would certainly give you a table of integrals. Okay, and you don't have to use it. You can, for instance, do that v bar one. You can do this one by using integration by parts. Okay, that's the integral of u dv equals uv minus the integral of v du. So you can use that, but you can also just look it up and that'll be a lot easier. Now, just as a little sidebar, I'm going to give you an example. Crap. Well, I'm going to take a couple of seconds to do the VP. The most probable occurs by maximizing the function. So I'm going to set the derivative of f of v equal to 0. So what I'll say is once I pull all the constants out in front, 4 pi m over 2 pi kt to the 3 halves, then all I get is d by dv of v squared e to the negative 1/2 mv squared over kt. All that equals 0. That means this stuff is irrelevant. So these things just cancel out. When I do the chain rule or the product rule, excuse me, I get 2v e to the negative 1/2 mv squared over kt plus v squared. Now I got to take the derivative of e to the x, and the derivative of e to the x is e to the x times the derivative of x. So I'm going to get negative mv over kt for the derivative of the numerator, and then, or excuse me, of the exponent, and then that times negative 1/2 mv squared over kt. All that's equal to 0. There's no way this e can make the 0. So ultimately, all we get is 2v is equal to, notice it was negative, so now I'm going to write mv cubed over kt. That allows me to cancel out one of these, leaving a 2 there with that, and ultimately that means I get v bar, excuse me, not v bar, but v most probable is equal to 2 kt over m raised to the square root power. Okay, so that's how you could do that one. You guys are free to go. We've gotten quite a ways into chapter 18. I will be skipping. You need to read all these things, whether I skip them or not. But especially you need to read real gases and changes of phase, vapor pressure and humidity. But I'm not going to require you, even though you might do it in a homework or a practice test, I'm not going to require you to calculate humidity on the test. I'm not going to require you to calculate evaporation. I might get you to conceptually explain boiling. That's fine. But the mean free path and the van der Waals equation, I'm probably going to allow you to do the van der Waals equation on the test, but I'm not allowing you to do mean free path or diffusion. So I'll write these in here before I put the notes up. So I'm just reminding you, you can skip calculations of humidity. Okay, they will be in your homework, but they're not going to be tested on. But you still need to read that. But you don't have to do 18-7 or 18-8. Okay. You do need to remember, as I told you before, though, and using the ideal gas law, if you use the ideal gas law for a gas that's over top of a liquid, like in a test tube or something, then you have to take into account the vapor pressure of the liquid that's below it. And that's what that table and that section on vapor pressure gets you. Nor will you need to calculate relative humidity. All right, I'll wait for the last person to go in case anybody has any questions, but you're free to go.
Have a good one, Mr. Younger.
You too. Sorry for keeping you a little late.
Yep, you have a good one, Mr. Younger.
Thank you. You too.
Professor Younger, for the previous lectures, were they going to be on your YouTube channel or did you have links to the actual videos?
Yes, they're on my YouTube channel, and the way that that's set up is the most recent ones pop up first, and they've all been posted there. The ones from today
Okay.
haven't been posted, nor the one. No, the one from yesterday was posted, but not the one from today yet.
All right, then. Thank you.
You're welcome.
Bye-bye.
Thank you. And that looks like the end of it. Bye bye, everyone.